All right. Welcome, everybody. Folks are joining us, so thank you very much for spending your time with us here. As people are joining in, this is the March version of Ask Mayfield Anything. And today we're going to be talking about microgrids and some of the challenges and solutions that we face. And so we'll talk about some stuff, big overview, and then also we have a specific job that we'll get into as well. So as you're joining, this is very much meant to be interactive. So we ask for you to send your questions in. This is the whole point of doing these, is to get you all to talk with us. Ask your questions. What we do ask is when you put them in, put your questions into the Q&A section, not the chat. So questions go into the Q&A. It just makes it a lot easier for us to make sure that we're keeping track of them. It's just an easier method to do that. So as we're going along, we'll keep an eye on those, ask questions throughout the time. We'll reserve some time at the end as well to make sure we have ability to ask questions. So with that, we'll jump in. And so my name is Ryan Mayfield. Thanks for joining, founder and CEO, Mayfield Renewables. And today we have Justine Sanchez, who is our solar+storage program director here at Mayfield. And Justine has more than 25 years experience to our team, or not with our team. She has more than 25 years experience that she brings to the team. And she's leading our energy solar+storage side of our business, working on system designs, educational workshops, technical consulting. And also Justine is on the NEC National Electrical Code Making Panel 13. And Justine, you're no longer the newest member. So, but thanks for making time and joining us here today.
Yeah, thanks for having me. I'm excited about this topic. Microgrids is my favorite thing to work on these days. And so I'm really happy to be here with Mike and of course, everyone else that's joining in. And we've got some really good topics to cover because they are complicated projects. But after a long time in the industry, it's kind of fun to be challenged and be dealing with all these different power producing sources and codes and equipment and controls. And so they're always exciting.
Cool. And we also have Mike Murray, who is a co-founder and the COO of Ageto Energy. And since founding in the company in 2017, Ageto has developed the Ageto ARC Microgrid Controller. It's a simple, intuitive, operator-focused microgrid control system. It's really the brains of the microgrid, and it's integrating, optimizing, and managing the multiple energy resources, and has been deployed on over 45 microgrid projects. And so these projects are maximizing renewable energy utilization by coordinating, dispatching, and monitoring a diverse range of energy resources. And Mike comes to us and he has a mechanical engineering degree from Missouri University of Science and Technology. And I didn't tell you this, Mike, but so I used to do a lot of the solar decathlons, and Missouri S&T was always there, and I loved those guys. They were that group of students was always rotating through, but it was a great group, and so very unique alma mater there.
Yeah, thank you, and thanks for having me, Brian. And thanks for also the Mayfield team for putting this webinar together. I always love talking about renewable energy and microgrid, so really looking forward to participating in this webinar.
Cool. So a little bit about Mayfield, just for those of you who may not know, we're a technical consultancy, and we really have, we have three main divisions of our business, and we're serving a broad range of clients. So we have our system design and engineering team working with EPCs and GCs on all kinds of solar and solar+storage projects. We have a technical content strategy and production division where we are working with manufacturers and other industry partners on talking about different aspects, delivering content, making content on those their products. And then finally, education and training, where Justine and I do a lot of our work, and we're doing professional development and certification training. We have workshops and different ways that we are trying to educate the industry as a whole. And kind of on that note, I'll also mention, for those of you listening live, next week is the NABCEP CE conference, and both Mayfield and the Ageto teams will be there. So if you have any questions, follow up, or anything like that, we'll be at the conference, and looking forward to talking with folks. Okay, so let's jump in and let's talk about microgrids. And really, I mean, the place to start is, what is a microgrid, right? What we need to define what a microgrid is before we can really start talking about it. And of course, me being kind of the code nerd that I am, I'll jump into and, use the code definition, the National Electrical Code definition, as a microgrid. We can use at least that as a starting point, and that helps, kind of set that foundation. What we're looking at here, we're going to mention that we have a nice project that we've worked on, and that we both Ageto and Mayfield were involved in. And so this is that project, and we'll kind of go through some of those highlights here in a little bit. But first off, microgrid, as it's defined in Article 705 of the NEC. So it's a premises wiring system that has generation, energy storage, and loads, or any combination thereof, that includes the ability to disconnect from and parallel with the primary source. So we were talking about this as we were getting ready for this call. And so there's some key things there. One of the things, Mike pointed out is it's that interaction with the utility. And so when you think about, there's a lot of gensets out there, right, they are behind an ATS, and they can back up some or part of, or some of, or the entire building. But those are behind an ATS, and they're not actually operating in parallel with the utility. So those are, I don't want to say simply, but they're not a microgrid. Because they're behind this ATS, they're not interacting with the utility. So most of our systems, I mean, nearly all of our systems that we're talking about here, are going to have some sort of energy storage involved, may or may not have solar, may or may not have a generator, but they have multiple sources of power, and interacting with the utility is kind of that key piece. I don't know, Mike or Justine, if there's anything you wanted to add on kind of those definitions.
I typically take a very encompassing view of the definitions for a microgrid. So like you said, interacting to the utility, or, a lot of these systems that Ageto is working on are completely off grid. So, they're in remote villages or communities that don't have a bigger grid to connect to. But if there's multiple energy resources that are operating off grid, then that is also a microgrid.
I guess primary source, like if you want to dive into the definition of a primary source, I mean, we always think of that as the utility, but I don't suppose it has to be.
Yeah, it could be a generator.
Yeah, sure.
But let's not get stuck on the definition of a microgrid. Let's jump into some really key topics.
Okay, well, I'm not gonna stuck on that, but I do. Kathy actually just already asked a question, which is great. So keep them coming, everybody. But so definition of a nanogrid. I honestly don't know if I could define that. Mike, can you help me out here?
There's all kinds of different definitions for sizing of the microgrids and nanogrids or picogrids. Nanogrids, I believe, are typically smaller, so like 10 to 20 kilowatts maybe.
Yeah.
Most microgrids that Ageto is working on, and that I think this is mainly focused on, is typical loads between 50 kilowatts and 10 megawatts. And then once it gets larger than 10 megawatts or 100 megawatts, like the Hawaii Islands, those are utility grids. Some people could call them a microgrid because they are islanded, but it just kind of depends on sizing of the system. Okay,
that makes sense. Okay, but as Justine said, we won't get too hung up on definitions. We can spend a lot of time there. So let's talk about the Ageto controller, the ARC Microgrid Controller. Tell us a little bit about that, Mike.
Yeah, thanks, Ryan. So Ageto is a microgrid control solution provider, and we've developed our product, the Ageto ARC Microgrid Controller, and that has a primary responsibility of coordinating and optimizing the different energy resources in a microgrid. So the ARC controller, like Ryan said, has been deployed to over 45 operating projects and has accumulated over 375,000 hours of operation since our founding back in 2017. So we've done quite a few different projects. You can get a feeling for the different types of projects in the link that the webinar can provide. And I guess how Ageto typically works on these projects is we typically partner with either a project developer or a solar EPC company, and we work with them to build, the microgrid, select the right assets, size the assets, and make sure it's a successful project. So that's what Ageto's approach has been, and this is where we kind of fit in this microgrid market. I guess also, we don't typically work on residential size projects, but we do a lot of, 3-phase 40-volt type projects. And the loads typically range, like I said, from 50 kilowatts to several megawatts.
Can I jump in for a quick moment? I would just say, so from my perspective, being a PV system designer, installer, and code person or whatever, going into this first bigger project, I wasn't even really entirely sure what the controller was going to do. And then ultimately, in my mind, what it came down to is that we had like an existing PV array with all these interactive PV inverters, like a bunch of solar edge inverters. And then we had our energy storage system from Blue Planet in this case. And then we also had a generator, and then we had the utility. And so to me, it was like the ARC brought it all together and actually had that ability to throttle back the PV inverters when the batteries were full. It can talk, I think, to the BMU it communicates with the Blue Planet energy system and sends its signals. It did have the capability of working with the generator. We ended up with a kind of a different route when we coordinated with the generator with that project, but with other projects, it could also talk directly to the generator. And then of course, it's telling the utility to microgrid connection, the mid microgrid interconnect device, when to open and when to close. And so it's, to me, it really is the brains of the whole system. And so, and it's an incredibly complicated and fascinating part of the job, I would say.
It's definitely fun. And the other way people sometimes, help define what the microgrid controller does is kind of like the conductor for the orchestra. Mm-hmm. So it's what's telling all the different energy resources when to play, how loud to play, and making sure everything's balanced in the system.
Awesome. Okay, so maybe we should get into some of these challenges. So we kind of, as we were preparing for this, we identified some of the challenges. I'm sure we're not going to cover every single challenge in in an hour-long conversation, but some of the top ones that we've seen, that Ageto's seen. And so so we can start with the asset selection, and so Mike, can you kind of talk us through a little bit some of these bullet points on this asset selection?
Yeah, definitely. Thanks, Ryan. And just to kind of orient the slide here, this is the Ageto home screen from our control system. So this is what would be displayed on the local control system, and this is where the operator or the facility manager would interact with the system. So they would be able to get all the performance information, alerts, and alarms from this one control screen. So we're going to start with the battery inverters, and those are the two devices that are circled there. And there's a wide variety of energy storage inverters on the market. They have a wide range of both price points as well as functionality. So depending on what your project is kind of where you need to be on that that scale of the energy storage inverters. So at the bottom, you have the basic inverters, and they can only operate in grid following mode, which is similar to like a PV inverter. But for some applications, that's great. If you're just doing utility rate optimization or energy shifting, you don't need a grid forming backup resilient power system, then that might be all you need, and you can save some money on that. Other inverters, though, can actually switch from grid following to grid forming in milliseconds. And then that way, if there is a utility outage, the entire facility can have backup power seamlessly. And the facility won't even notice that the lights flickered. And then other inverters, they can switch modes, but it might take over a minute to start up in grid forming mode. So depending on what you need and what the facility requirements are, there's a wide range of inverter selections there. And then when you're integrating into systems that have generators, some of these have more advanced capabilities like droop control or synthetic inertia. And that allows you a little little bit more flexibility in how you integrate the generators, and also can improve the performance of the system, prevent different blackouts, et cetera, by having these more advanced capabilities. The Ageto system, though, works with these inverters and their capabilities, so we can't create capabilities in an inverter that doesn't exist, so we can't make it switch faster, but we can leverage and maximize the functionality of these different inverters. And then there's the practical stuff on the integration. You want to make sure that the battery inverter and the battery DC voltage ranges match up, and that you have 480 volt 3-phase output or single phase, whatever the site needs. So those are the main things that I kind of look for in energy storage inverters for microgrids.
Hey, Mike, I have a question for you already. You mentioned droop control. Was that what,
Yep.
and then something about inertia? Could you
Yes.
get into those just a tiny bit more, maybe just a quick?
Yeah, so this is primarily for off-grid systems when we're working with generators with a battery storage system. So like our project up in Shugnak, Alaska has both grid forming generators, but also a grid forming battery system. And they're both operating in grid forming mode together using these droop controls to balance the power flow between them. And then the Ageto system sits on top and kind of like balances these together so they work seamlessly. And what that gives us is if there's a fault in like the generator has a fault, turns off immediately, the battery can seamlessly pick up the entire community load and there's no power outage. And then the generator can start and the next one can start and help support the battery, but it prevents blackouts like that.
Okay.
Interesting. Cool.
So then,
yeah, moving on to the battery.
So batteries are the widest range of options right now out there. There's, and batteries is probably a very limiting term. Currently, it's more energy storage, because it's not just lithium-ion batteries that we're working with. It's also flow batteries, either vanadium redox or iron flow or zinc bromide, or there's all kinds of different storage mechanisms, including flywheels. But some of the parameters that kind of affect selecting the batteries is what you're kind of hoping to get out of the battery system. So one that we run into a lot is the nameplate versus nominal rating of the battery. So some batteries allow a full 100% depth of discharge. Meaning if it's a 100 kilowatt hour battery, you can use a full 100 kilowatt hours of storage every day. Other batteries that only have a limited depth of discharge, so they typically have a recommendation to run between 10 to 90% or 10 to 95%. And with that limited range, your 100 kilowatt hour battery might only be 80 kilowatt hours. So just making sure you understand all the specifications when you're helping size a system. Another key consideration on the batteries is their C rate, and that's how fast a battery can discharge their capacity. So in the energy storage space, they typically range from 2C down to 0.25 C. But the common ones are either 1C, which means you can fully discharge or charge the battery capacity in 1 hour, or 0.5 C, where the full discharge would take 2 hours. So that's one thing to look at. Usually these projects, and especially off-grid microgrids, need at least a 2-hour discharge to for a standard C&I microgrid application, but some unique applications only need 20 minutes of backup power. So there you could get away with like a 2C or a 3C battery, which can save money. Another thing to look at is beginning of life versus end of life. So the beginning of life rating is how much energy you have when new, and then end of life is after 10 years. So typically in the C&I space, commercial industrial, we're typically looking at beginning of life, with the end of life calculations more common in utility scale projects. Now to get into some chemistry, lithium-ion batteries come in 2 primary chemistries that are commercially available in the energy storage space. NMC, and that stands for nickel, manganese, cobalt, and LFP. And LFP is sometimes pronounced as LiFePO, which stands for lithium iron phosphate. But LFP is kind of winning out over LiFePO for terminology. NMC has really been the dominant chemistry for both stationary and automotive storage for the last 5 to 8 years. But LFP is quickly growing, and I feel it will become a dominant chemistry going forward. The price point can be better, but then there's also, you don't have the issues around sourcing cobalt and nickel and other rare metals. So LFP is typically a little bit lower price and is really gaining popularity. The downside with LFP is it is a little bit less dense, so you need more space for the batteries versus NMC. And then there's a wide range of pricing for batteries and integrated DC blocks of the storage. Some things to look for when you're looking at quotes and pricing is cycle count, warranty, safety certifications, and also most importantly, the support that the company will offer.
So I'm going to go.
Oh, go ahead.
I was going to go back a little bit on, you had mentioned the C rate, and I know that's an interesting one, and I guess one of my mind immediately went to is I guess that's somewhat a function of the inverter that you're connecting to as well, just in terms of how much it can charge and discharge. So I'm just curious, how much you all are seeing a variety in C, just in applications. Does it vary a lot for the customer that's trying to do backup versus the client that's trying to do maybe some more demand management type offsets?
Yeah, I guess there's kind of two C rates that, now that you mention it, kind of depends on the sizing of the system. So there's a battery rated C rate, and that's a max that it's rated for. But then there's the installation and the actual C rate. So you can have 300, 400 kilowatt hours of battery behind a 100 kilowatt inverter. So it's the battery system, I guess in that case would be 0.3 C. But the batteries might be rated at 0.5 or 1. You just want to make sure you don't overload the batteries with the inverter.
Sure. Yeah. So I guess it's just a function of individual components versus the system as a whole.
Mm-hmm.
Yeah.
One thing I was going to add on to some of the things that we found out in the project we worked with you on was how we chose our batteries. And there was a couple different factors going in that I didn't realize, or when we went in, I didn't realize until we were in the middle of it. And one was not all energy storage systems can utilize the full capacity of your array. So we had an existing array up there. It was 255 kW. We were looking at a couple different battery options, and one option would have required us to segment about 100 kW of that PV off the energy storage system. It couldn't absorb that much through the through the battery, basically, or maybe it's I'm not exactly sure what the limiting factor was exactly, but that was one thing. And then the other thing was indoor versus outdoor. So some of these battery systems are meant to go outside. And in this case, we actually had room and a utility room and space. And we had to really weigh both those details out, because going outside would have been actually kind of nice for some areas, but we would have had to put vehicle impact protection out there as well. And it would have eaten up space in their outside parking lot that they didn't really want to give away and plan for and stuff. So there were some other details that went into our battery selection beyond C rates and the chemistries. We did go with LFP because just the non-flammable aspect of that was key for this. This project they're worried about earthquakes, and things happening during an earthquake. So we had a lot of thoughts around safety when it came to this particular project. So
there's a multitude of factors in all these projects, and I'm probably only hitting the top 20% right now.
So yeah, we'll dive more into that specific project. But yeah, this is kind of right along the lines of what you were talking about, Justine. So now we have more asset selections, and so inverters, new versus existing. Kind of how do you see that playing out on these systems that you've been involved in, Mike?
Yeah, the solar inverters, is always a key point or key asset in all these microgrids. We're seeing more and more often where we have brownfield sites or sites that already have had installed solar maybe 10 years ago, and now they're coming back and installing energy storage as well. And sometimes you have a site that has a old, 10-year-old PV powered energy store or a solar inverter. Those were very common 10, 15 years ago, and they take up most of a room and they weigh 1,000 pounds. But you can't get support on them anymore. You can't integrate to them right now because they don't have the control capabilities that the modern inverters do. So on most of those, we are actually just removing them and replacing them with an upgraded modern inverter like SolarEdge, SMA, CPS. Most of the brand name solar inverters out there in the commercial space have the control capabilities that we need to allow us to curtail or reduce the output of the solar inverter to allow it to seamlessly integrate with the microgrid. One thing you might also need to check out is if you do replace a solar inverter, see if the string voltages are still going to match with the new inverter, and also see if it'll trigger any requirements for like rapid shutdown or coming up to code on the solar installation. It's probably still the best thing to do, but just be aware of those potential costs for the project when you're integrating with solar.
Yeah, and that's definitely something we've been seeing as systems are aging. We're starting to see some of those inverters, inverter manufacturers that it's either really hard to get the support or it's impossible to get the support. And so people choosing just to take out that old inverter because it's a 12, 15-year-old inverter. That's hopefully what was built into the system life anyway. It was kind of put into the pro forma, hopefully. And so, yeah, but those are, what that alone becomes a project in of itself. Just what can you replace, a 600 volt 480 inverter, not the easiest thing to get your hands on sometimes or at all. And so, yeah, what implications does that have?
Yeah, for sure. And the plus side is, those old PV powered inverters have probably 800 pounds of copper. So the recycling value will probably pay for a new solar inverter. I did see a couple questions on the microinverter usage, and Ageto does not yet have any project with microinverters. Typically, they don't have the curtailment and control capabilities built in from the factories, though I do know that's being worked on for a few of these different microinverters. What is a possibility to do is to actually use contactors to kind of segment off parts of the solar array to basically just open the contactor so we can't get any more power from these PV inverters, the microinverters, and that will allow us to modulate the output of the solar array. It's not as precise as with curtailment commands over Modbus, but it's a way to make it work.
So in that situation, it's kind of an all or nothing kind of, in essence. It's
or we can we do like one or two groups maybe.
Okay.
So then you can do half or all.
So you can start to segment the array instead of taking them off. But as far as that circuit of microinverters, it's either on or it's off.
Yeah.
Okay.
But they are working on that because they've seen the need.
Sure.
And there's definitely a spot for microinverters.
So can you dive a little bit more into, what you were talking about, the curtailment capability? So when I hear that, I'm thinking frequency shifting. Is there more to it? Are you guys doing something different? And you mentioned some of the newer inverters. So what are you doing to curtail that? Because frequency shifting seems a little kind of brute force method as well.
Yeah, that's obviously very popular, in the residential space, but most of the commercial inverters have curtailment capabilities over Modbus. So basically we just send the inverter a command saying reduce to 50% output, 40% output, and they will adjust the power electronics internally to just reduce the amount of solar that's allowed to pass through. So they aren't actually burning it off or anything. It's just actually how they shift the power electronics inside the solar inverter. And that can happen on a second by second basis. So we'll balance the current facility load with the solar production every second.
Okay. Is that part of the newer listing, the updated UL 1741 listing? Is that just part of what this is now?
I'm not sure.
Okay, cool. And then generator integration, which is a big one, and that was we can talk, I think, quite a bit. Justine and I can probably talk a lot about that on our project specifically, but why don't we talk a little bit about it in general first?
Yeah, so I guess, kind of similar to the energy storage inverters, not all generators out there have the same capabilities. So in the commercial side space, 50 kilowatts to 500 kilowatts, the standard offering for many years has just been a grid forming or ISOC inverter that's typically behind an ATS. And this is a very common thing in all these backup power systems. But it really causes a lot of compromise in the functionality of the generator with the microgrid. So typically what we're pushing for in these microgrids is for a seamless integration. And that's where we want the generator to be able to parallel and synchronize to the microgrid bus. And this will allow the microgrid controller to tell exactly how much power is needed, similar to what we do with the solar inverters and the energy storage system. So more and more generator companies are fitting generator controllers to their gen sets that can have this functionality. It's typically a $5,000 to $10,000 upgrade on the generator for this paralleling capabilities, but it greatly reduces the functionality of the microgrid to allow that. Because if you don't do that, the ATS is kind of the limiting factor, because the Mayfield or the OMD project that we've been talking about, the ATS had to stay in there because it was part of the emergency system. So the way we had to integrate it is we rerouted the normal side of the ATS to the microgrid panel. And then when the batteries are low and there's no sun, we would actually open a load drop contactor, and that would black out the normal side. And then the ATS would go through its normal functioning to have the generator kick on, and it'll switch over to emergency operation mode. But every time that happens, there's a short power outage and it's not a seamless experience. Whereas if we could upgrade the generator, then it would be a lot more complete solution.
So I was going to say, we have a diagram coming up that might help folks kind of visualize what you're talking about. And so we could talk about that a bit more. And I wanted to ask that, so if, what is that called? Is that called a grid following generator? I mean, like, what would be the term you would look for in that capability? But if you wanted to be able to parallel it with, instead of keeping it separate.
So the terminology between the solar plus storage space and the generator space is very different.
Yeah.
I used to work in the generator space, so we have a lot of experience with that. But for energy storage, it's grid forming or grid following.
Right.
And with generators, it's ISOC, which is grid forming, or base load, which is grid following.
Oh.
Also, sometimes base load, which is a generator term, is called demand response mode. So there's a few different terms, but basically you want to be able to say the generator can ramp up parallel with a energy source and connect to it while it's running.
So you said demand response or base load.
Or base load
would be the
base
two
load's
terms.
the most common.
And that's desirable. Okay, but what if we want to run the generator on its own for some reason? Would you be able to?
Yeah, so most of those generators that have base load capabilities can also operate grid forming or ISOC mode.
Okay.
And many of our systems will have it set up and programmed where if the battery system has a fault or can't turn on for some reason, or the solar isn't working, we'll actually default the generator back to ISOC or grid forming mode to power up the facility. So we always have that, multiple layers of automated redundancy in our system.
That's great. Because I guess, one of the things we're always worried about is like that PV trying to push into the generator, right? But if you have
and that's where that curtailment comes in.
Okay.
So, we have a few systems that are just solar diesel systems and no energy storage. So in that case, we'll have to keep the generator running to be the grid forming asset in the system, but we'll curtail the solar on a second by second basis to provide a minimum loading set point, typically 20% or 40% loading on the generator, and that will allow it to operate with using less fuel, but also efficiently and not cause any performance issues of underloading or reverse powering the generator.
Excellent.
Yeah, that's super cool. Because we always think you can't do that, you know.
Right. I mean, that
Yeah,
was
and with the bigger systems like, you know, the commercial scale systems, it's become a lot more common to do that.
Mhm.
Yeah, and I remember seeing years ago now, I mean, these systems that were doing, they were PV plus generators. And so, and the whole idea is reducing your diesel consumption. And so, yeah, it's interesting that the more and more systems are able to do that. All right, so I think, so that kind of helps us look at the kind of those components. And so the next thing that we're gonna just talk about, you know, this challenge of interconnection AHJs. So I did see a question that came up about asking about interconnections. And so Justine, why don't you walk us through kind of what we're looking at and kind of what the implications here are of what we're talking about with this ATS.
Yeah, so this isn't really an interconnection question, but it is definitely, or a topic, but it definitely is an AHJ topic. So
Sure.
what happened with our system, we went into where this facility had what's called an emergency panel. Okay, and so this panel is specifically put in place for like serious like health or safety issues, like think exit lighting, you know, so it's a place of assembly where people might need to, the power goes out and they might need to get out of there for whatever reason quickly and know where the exits are. And so there's going to be certain circuits within an emergency panel that are legally required to be backed up by an alternate power source. And generally that's going to be a generator, or historically that's a generator. And so there's different NEC articles, like Article 700 is specific to emergency power systems. And there's very specific requirements when it comes to automatic transfer switching that have to be listed for emergency systems. And so if you start diving into these, you know, microgrids for resiliency for commercial facilities, you might run into an emergency panel and have to comply by the rules of Article 700. In this case, we did. So the AHJ said, hey, this was already set up with an existing 150 kW diesel generator, already wired to an automatic transfer switch, listed for emergency systems. There's a whole separate ATS for an optional standby panel, which has all the other circuits they wanted to back up with the generator as well. And they had to keep those separate. And so there was 2 ATSs in the system. And when you do all this kind of work, like way back when, they did all this like selective coordination and testing of the system to make sure things turned on in the order that they were supposed to, nothing got overloaded or tripped things offline and so on. So what we ended up doing is keeping that generator tied to its automatic transfer switch the way it always had been on the emergency side of the automatic transfer switch. And so none of that changed, okay? Our generator's the same, the automatic transfer switch is the same, it's still feeding the emergency side of that transfer switch. So if the grid goes down, or whatever we're normally powering our load panels with ceases to be there, it just flops over and connects to the generator. And the generator directly feeds the emergency loads, okay, or in the emergency panel. But what that meant for us is that we had to keep it isolated from our energy storage system. And so we couldn't use that excess generator runtime to charge batteries because we had those 2 systems completely isolated. And so if you look here, we have our microgrid panel, okay? So you see your PV array, we're not showing our individual string inverters in this case, just assume there's an AC output. It feeds our microgrid panel, okay? And also feeding our microgrid panel is our energy storage system. The output of our battery inverter feeds our microgrid panel. And then our utility connection feeds the microgrid panel. And so those items are what's connected to the normal side of the automatic transfer switch. And so under normal operation, that emergency panel, and there's actually another panel not shown here, the optional standby panel, is being fed by our microgrid panel. So solar, battery, or grid. And so if those go away, or if, we have all this controlling happening, and then if it sees no voltage, basically on that side of the automatic transfer switch, boom, the generator starts up and feeds the backed up loads, the emergency backed up loads like they always have. Is that good enough?
Yeah, and I think that the big thing that, you know, the unfortunate thing, I guess, here, and this kind of plays into what Mike was just talking about with the generator, is the generator and the energy storage system never see each other in this situation, which was quite unfortunate, just because that's what we really wanted. That, and so in this very specific case, would have loved for the generator to kick on, serve the emergency loads, the backup loads, and at the same time, there would have been enough capacity in that generator to charge the batteries. And in reality, it would have been if we could have made it work, that would have been a better situation. The generator would have run at a higher efficiency value, and then would have been able to cycle on and off and save even more fuel, because that was one of our big things on this project itself.
Yeah, this whole change, because of the HJ said, hey, this is an emergency system, you have your stuff to be emergency rated, this caused a complete redesign on our side, and we had to remodel everything as well, because we had always assumed that the generator would be able to charge those batteries. And so when we went into our fuel usage and for our scenarios that we were trying to model for, all that fuel usage did go up as a result of this isolation of the generator. We still were able to make our goal, and that goal for this particular project was to run for 2 weeks with 1,000 gallons of diesel fuel with our 250 kW PV and our energy storage system, to run 2 weeks without the utility being present. And even with isolating the generator, we're supposed to be able to still do that at any time of the year, which is nice.
Right. Cool. So yeah, so like you said, that's not really an interconnection thing, but that is definitely, a challenge, and one that, catch it earlier. And so, do you have emergency loads? Do you have truly an emergency system, which has a completely separate section in code that you have to adhere to, and can have big implications.
I guess one thing on that too, Ageto's working on a project in the Northeast right now, and we're actually going to use a solar+storage system for legally required loads. And it's going to do a site certification with UL to get that certification for that project.
Nice. Yeah, that's
so
a really good point.
The battery is running the fire pumps, the lighting, the elevators, to make the system, legal for the local code.
And how easy or expensive is it to get that field certification, if you can speak to that at all?
It's not inexpensive.
Yeah, okay.
I think it's tens of thousands of dollars per site.
Mm-hmm.
But some of these projects are $3, $4, $5 million projects, so
certainly, yeah,
probably well worth it. And then you don't have that one generator out back that has to run every week and do oil changes once a year. It really can make a better installation.
Yeah.
Cool. So let's talk a little bit more about some of the National Electrical Code, the articles, and this maybe we can get into some of the interconnection stuff here. So Justine, why don't I have you take the lead on this slide? I know you've talked to it before, so.
Yeah. So one of the things that we were doing simultaneously with that project was developing a class that went over the NEC and energy storage systems for 2020 code. And all I know is, like, when I first got into this a couple of years ago, I was just flipping back and forth through, like, wait, 690, 706, 705, 710, 480, where do I go for the answers? And so I spent a lot of time like drilling into, like, okay, the PV stuff, so you're obviously going to find in 690, energy storage stuff, like what is all covered in 706, and which circuits are we talking about, and which pieces of equipment do you have to go to 706 for information and the requirements for 2020 code. And so we kind of overlaid that on top of this diagram. And then you get into, like, well, how are all these things coming together? Like my PV array, especially on an AC coupled system, my PV array is coming in to say maybe it's a microgrid panel. Here we're calling it a backed up loads panel because this is an old school diagram. But where those sources come together is covered by 705, like interconnected power production sources. And so you got to go to 705 for those rules. And then if you operate in standalone mode, which is like, all of a sudden you're off grid because the grid went down, you can apply the rules of 710. Although some AHJs may actually require you to apply 702. That's a whole nother, that's historically for standby generators. But you might look at this as an optional standby system more so than a standalone system, even though there's code language and pointers within 706 that send you to 710 for the rules of when you're in standby mode and what has to happen there as far as capacity and automatic transfer switching, and just even like how you interconnect with a particular breaker that's not marked line and load, if it's a load side connection, blah, 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 all kinds of little rules in 710, not a lot, but definitely some. And then what if you happen to be working with lead acid batteries? Then the rules of 480 kind of make a bit of sense to apply as well, because there's specific safety factors with lead acid batteries, like corrosion prevention and items that have historically been for lead acid batteries that you'll find in 480. So there's a lot to consider when it comes to just the NEC, but there's also then there's fire code, which we'll talk about next. So I would say it's a really challenging time, exciting time to be working in energy storage and microgrids, because you get to apply all these code sections and they're changing. So now that I'm on the NEC code making panel 13, and we cover 480, 706, 700 for emergency systems, 701 for legally required standby systems, 750 for energy management systems, which I haven't even shown on here. Fire pumps are actually, I think that's for, I remember, I forget, 445 is generators, and fire pumps is, I forget which one that is right off the top of my head right now, maybe 485. Don't quote me on that. And so, and that's all changing for 2023. Second draft was just dropped yesterday, actually. So everyone can go online and see what the second draft of the 2023, which is really close to finalized for 2023 code, and how some things are changing with all these articles pretty much in the next edition. So and then you have new equipment, and new use cases coming up. So it's a lot of newness is what I gotta say when it comes to adhering to the codes and standards with this equipment, and all the different microgrids for resiliency concerns that are coming online. We're in a new paradigm.
And also, Justine, a lot of the AHJs out there haven't seen this before either. They're probably going through their first energy storage installation. Mm-hmm. So, having someone that they can turn to and trust on, what this actually means and how to implement it was probably really valuable as well. Well,
we certainly enjoyed solving these mysteries as they came up.
Yeah, and that was definitely a big part of it, was, interacting with AHJ kind of and quite honestly answering some of those questions. And it was, that question that came up of the emergency panel, that was definitely one better to ask ahead of time. I don't think asking for forgiveness would have gotten us anywhere in that scenario, and then that would have been a major issue of reworking. So yes, that was definitely a good aspect. So real quick, Justine, if you can, mention fire codes. And so,
Absolutely.
I know that's another thing that you've really researched, and you have a couple classes just to throw that out to folks if they're interested in learning more about this. Justine's put together a lot of work on that. Yeah, so kind of some of the high level fire codes that are applicable here that we should be, the attendees should be thinking about.
Yeah, absolutely. So the NEC is going to cover our electrical requirements, right? But then there's a whole other set of requirements when it comes to fire code that are going to be covered either in the IFC for commercial applications or the IRC for residential applications. And I should say, if you go over a certain threshold, you might get pushed over to the IFC. If your installation's big enough, you have enough kilowatt hours, then you might have to apply by the IFC, so IRC, IFC, so IFC for commercial, IRC for 1 and 2 family dwellings and townhomes, residential to a certain point. The IFC rules are harder to comply with, right? Because they're thinking about larger installations and everything that could happen with a larger installation. And then some areas actually don't choose the IFC. They actually go with the NFPA 1 fire code. So there's certain states that go by NFPA 1 for fire code, and other states that go by the IFC to complicate things further. So you have to figure out which your jurisdiction actually goes by, and then dive into those rules. And not only whether it's just IFC or NFPA 1, but what edition. Are you in 2015? Are you in 2018 or 2021, which is going to be the most stringent rules when it comes to energy storage systems? And these types of rules are like, okay, vehicle impact protection, the wall, your fireproofing on your wall assembly. Do you have a 1 hour or a 2 hour fire rating on that assembly if you're going to put energy storage within a room, or ventilation requirements, or, oh gosh, there's many of the maximum allowable quantity within the room, the maximum per unit, and then spacing that's required between units, because what they're thinking about is fire, right? It's fire code. And so there definitely has been a lot of stories of late about fire with lithium-ion batteries going into thermal runaway and causing fires. And so these codes and standards are thinking about that and trying to basically kind of attack the issue from two different vantage points. One, what can they do to prevent fires? Like make sure that we have thermal runaway protection within our energy storage systems. But two, if there was a fire, how do we make sure these installations could kind of like mitigate the impact? So if you think about a room with a fire rating, like a 1 or 2 hour fire rating, it can hold the fire for an hour or two before it spreads to the rest of the facility. So it's when you start reading these rules, it's kind of like, wait, why do they require this? And why do they require that? It's like they're trying to stop fires. But if there was a fire, what can they do to like minimize the damage and save lives? So I'm a big fan of the fire code. Some of them are a little, for some people over the top, but honestly, with the amount of fires that have been reported with different lithium-ion battery products, whether they're energy storage systems like stationary storage or EVs or e-bikes, or even like hoverboards or phones, like we're not the only industry dealing with the potential for flame from lithium-ion batteries. And so I'm a pretty big fan of this effort to make our installations safe. The other document we have up here is NFPA 855, which was put out in 2020. And that is really what informs the 2021 versions of the IFC and IRC and NFPA 1. So California and New York are really kind of the leaders when it comes to requiring these most current up-to-date rules with energy storage. And this book was kind of like NFPA 855 was after we had that big accident in Arizona with the 2 megawatt plant, sending 9 first responders to the hospital, 3 of them with serious, longer lasting injuries. Like it was a big deal. There's a lot of attention on energy storage and how to install them safely. So NFPA 855 is the standard for the installation for stationary storage. And there's a ton of information, and it's kind of the latest and greatest when it comes to the rules. And then the other IFC and IRC from 2021 pull out of the document to make their rules. So I'll stop there.
Okay. But plenty more to talk about, I know.
Yeah.
But yeah, that's great. So thanks for that overview. And we are, getting close to the top of the hour. So I want to make sure that we are, looking at some of these questions, answering. I saw Mike, you've been answering some. Thanks for throwing those in there. Real quick, I did see one, question, or Justine, you mentioned modeling, doing some modeling, and we have used. I guess the answer is kind of it depends. What are you trying to accomplish? What is the use case? And so Energy Toolbase is one that we like and we use. And then the other one that we've been using is Homer Grid specifically. They have kind of different functionalities. And so that's kind of the two. And I don't know, Mike, if you've run across any others that you like or anything.
No, we're a pretty big Homer shop here at Ageto, both Homer Grid and then also their original project or product, the Homer Pro for off-grid systems.
Yeah.
Homer gives us that flexibility to work with generators a lot.
Yeah,
more
exactly.
Modeling for.
Yeah. That was for us. I mean, that's what we're seeing is, quite honestly, we're seeing a lot of these resiliency type projects. And so, real quick, the one that we're looking at here, we've been talking about it a lot, and we should mention the Oregon Military Department, Sunlight Solar out of Bend, Oregon, who did the installation, and then Blue Planet Energy, who provided the storage aspect of it. All of those folks were highly involved in this project. So a lot of lessons learned. Justine has a number of notes that she's taken and implemented on that. But those the resiliency projects are ones that we're seeing more and more, and it's, you know, quite honestly a function of the natural disasters. You know, here in Oregon, this project is in Oregon. As Justine mentioned, we're overdue for our 500-year or more earthquake event, and so we're expecting some really major catastrophes if and when that hits. And so this was part of OMD's mission, was to create, as Justine mentioned, a resiliency project where this facility can operate with its backup loads, not the entire facility, but its backup loads can operate for two solid weeks without the utility present. And so that's kind of the gist of that, you know, a little background on that. So I'm trying to also read some questions over here while we're going to. So yeah, go ahead, Mike.
I was going to say, one thing that we can kind of touch on here is there's been a few questions about the interconnect device for these systems, and you can actually see it in the small screenshot picture at the top there. But it's typically a utility grade protective relay for these CNI systems. It's measuring the voltage, frequency on both sides of the contactor or motorized circuit breaker, and then if there's a fault on the grid, it'll isolate it. The microgrid controller will get feedback from that, and then we can black start the system in off-grid mode.
So I saw that question. I see that's gone now, but there was, you know, asking about the black start and the inrush. I'm curious kind of what that answer was.
Yeah, I can expand on that a little bit. So it like a lot of these questions or answers I put back in there, it depends on the energy resources. So like I mentioned with the inverters, some are a lot more capable than others and have a lot more functionality. So some of them are able to, you know, black start and deal with a fairly large amount of inrush by ramping up the voltage at the right rate so you don't overload the current rating of the inverter. And then you can actually, you know, with maybe like 100 kilowatt inverter, energize a 400 kVA, 500 kVA transformer. So it's typically not too big a deal if you're going from, you know, black start, and the inverters have that ramp built into them.
Nice, great. So yeah, so we are running up on time here. So you know, we didn't get to talk a whole lot about our project, and I think the three of us probably could spend more than an hour on just that project alone. Some of the things that we've learned, but some of the big key takeaways, and we've already mentioned a lot of this, is, you know, talking with the AHJ, the interconnection. That was actually, I don't know how to characterize that one. So, you know, Mike mentioned the existing PV systems already, you know, are going to very often be under a net metering agreement with the utility. You start throwing in storage. What does that mean? What do they care? How do they care? What does disconnecting devices, all those kinds of things. So those are some early ones that we had to deal with. And, you know, it was great that we did, because I think as long as that project took, the final thing was getting the utility to sign off on the installation. So, you know, make sure that that's also correct. Codes and standards, of course, are huge. And then, you know, choosing your components, and, you know, we put in the comment, if you're investing the best, it's, you know, really important that this equipment is going to be working. If there are issues, you have that response from the manufacturers, and all of the things that, you know, we've seen these out in the field, and you know, it's important to consider when you're looking at the entire life of the system. I don't know, Mike or Justine, if you wanted to add to that one at all.
It's a great summary.
Okay.
Definitely, you know, there's a lot of moving pieces in these systems, and, you know, really make sure you understand how everything's going to work together and what the trade-offs might be between selecting different systems in the overall microgrid project.
Yeah, and I guess I just can't say enough about the team. Working with Sunlight Solar and Blue Planet and Ageto and the guys, the folks at Nesmith Readiness Center, everyone was just the top of the line. It was top notch, incredible installation. Once we pulled all these, this whole project took like 33 months between like concept to completion or something like that. And pushing through every step of the way, working together, and making the project actually happen, and then having the installation as clean as it was. I've never seen such I honestly say, like a nicely laid out wiring, like of some pretty beefy components and control wires and contactors and relays, and beyond just the usual electrical stuff. I was just beyond impressed with the Sunlight Solar team, in particular the install team, and also everyone else that was involved in this project. So we just feel really proud of the work that everyone did and the end result. And I feel like we have a lot of new friends now too.
Yeah, and I think, obviously the team that people assemble, that those of you out there, it's really important that the communication and talking about it, because there were plenty of speed bumps on that project along the way, and it wouldn't have happened if everybody hadn't stepped in and done their part, and sometimes done not necessarily what even maybe was their part to begin with, but took on that ownership.
That's the thing I would say about these microgrid projects. Expect to do a lot more work than you think you're going to. Like, everybody's going to have to put in some extra hours to make these successful. I mean, maybe someday we'll be really good at forecasting how many hours it's going to take, but it seems like there's always new challenges that come up, and everyone has to pull together to come up with a solution and push forward. So kind of expect that going in if you're going to get in this kind of work. It's not cookie cutter for the most part.
Sure. Well, cool. Well, we have officially gone over time. So for those of you who submitted questions, we weren't able to get to everything. I know, really appreciate it. We'll see if we can reach out and answer some of those, but you're also more than welcome to reach out to us directly. Here's all of our contact info. You can get to us, a hold of us directly this way. But yeah, and so please feel free. Really appreciate your time, Mike, Justine. This is great. And as I mentioned, we can probably spend many hours on any one of these topics. So I appreciate it.
Can I add one last thing?
Of course.
So we will be talking about at least the codes and standards when it comes to energy storage next week at NABCEP. So all that stuff I was going into, you can come and hear another like 90 minutes worth of it next week live, which is really cool. And Ageto will be there as well, and our other team members from Mayfield. So anyone that's on the call and wants to talk more about microgrids or these codes and standards, please come find us, because it's not often we get to be together, right? So
Right.
Let's get together.
Cool. Well, thanks everybody. Mike, appreciate it. And yeah, thank you all for joining, and let us know if there's any questions or comments, any way that we can help you.